Now we're going to solve another recurrence relation. It's of the form a sub n is equal to a sub n minus 1 plus n, where n is an element of 2, 3, 4, etc. Now with this, I'm going to start with an initial condition of a sub 1 is equal to 5. So a sub 1 is going to be my first term, and it's 5. Now, according to the recurrence relation, a sub 2, if you look up here at this formula, a sub 2 is a sub 1 add 2. So I'm plugging into the formula for n equals 2. Now, since a sub 1 is 5, a sub 2 is 5 add 2. Now, I'm just going to leave it. I'm not going to combine it and call it 7. Instead, I'm going to break it up into a 4 plus a 1 plus a 2. And hopefully it's going to become clearer why I did that after we do a few more iterations. Now remember, don't simplify much, but rather group terms together that come from the same part of the equation, and up here the same part of the equation is this plus n. So now let's do a sub 3, and a sub 3 is, according to the recurrence relation, a sub 2 add 3, but a sub 2 is 4 plus 1 plus 2, so it's going to be 4 plus 1 plus 2 plus 3. Now this 3 came from the same place as this 2. It came from n up there. So now I'm going to group those together, and I get a sub 3 is 4 plus 1 plus 2 plus 3. Well, a sub 4, according to the recurrence relation, is a sub 3 add 4. And since a sub 3 is 4 plus 1 plus 2 plus 3, I'm going to add another 4. I group that 4 with the rest, and I get a sub 4 is 4 plus 1 plus 2 plus 3 plus 4. Now I started looking at this. A sub 4 is 4 add 1 plus 2 plus 3 plus 4. A sub 3 is 4 plus 1 plus 2 plus 3, and I started thinking about that index and that last term. By the same token, a sub 2 is 4 plus 1 plus 2, and there the index still matches with the last part of the sum. So after I think about it for a little while, I reach the conclusion that in general a sub n is 4 add 1 plus 2 plus 3 plus ... plus n. But now I look at that piece and I say, that's something I should have in my back pocket. That's the sum of the first n positive integers. Now, this is not solved yet because I have ellipses there. And to have a formula, you need a formula without ellipses. Well, it's easy enough for me to turn 1 plus 2 plus 3 plus ... plus n into my back pocket formula, n times n plus 1 divided by 2. And hence, I have now solved that recurrence relation. That is, I have a formula for the recurrence relation. And it's good for any n element of the natural numbers which I'm going to remind you is the set 1, 2, 3, 4, 5, etc. Notice that at the very beginning, my recurrence relation was only good starting at 2, but now after I've solved it, it's good for starting at 1. In other words, it picks up the initial condition. Now, if I want, I can check the initial condition. If I were to stick in 1 into this formula, I would get a sub 1 equal to 4 add 1 times 1 plus 1 all over 2, which lo and behold does simplify into 4 add 1, which is 5. And that checks with my original initial condition, which gives me a warm, fuzzy feeling that I've solved this correctly. Well, that's all I have to say about this particular problem.